We have studied a number of bias circuits to bias a transistor at a constant drain current instead of fixing the gate source voltage. Okay, and they're all shown here. There are different choices for where you sense the current and where you apply the feedback to. Based on that, you get 4 different types of circuits. Okay, now these circuits, they use these current sources which are required. Now of course, using a current mirror, we can generate a number of current sources from a single current source. So that is possible. But these current sources are usually more easy to get when you have an integrated circuit. Okay, the economics are slightly different for integrated circuits and discrete component circuits. When you have an integrated circuit, the number of transistors doesn't matter. Okay, it's the total area that matters. Whether you use a transistor or a resistor, the cost is more or less the same because it's basically based on the area that's occupied by the component. In fact, it could be that in some processes a resistor is more expensive than a transistor, or a capacitor is more expensive than a transistor. Okay, now this is usually not the case when you have discrete component circuits, when you buy these discrete components and build circuits around them. Okay, there typically passive components like resistors and capacitors are very inexpensive, whereas transistors are a lot more expensive. So you would not use another transistor to realize this current source. Okay, and also you may not get sufficiently good matched transistors to realize these current sources and so on. Okay, especially in discrete component circuits and sometimes in integrated circuits, there is some motivation to not use a current source like this for biasing. Okay, so let's see what else we can do. I'll take one of these as example, but exactly the same principle works for anything else. Okay, let me for illustration take some numerical values. Mu1 Cox W by L to be 100 microampere per volt square and threshold voltage of 1 volt, and let me assume that this current is 200 microamperes. Okay, and if you calculate, VGS will come out to be 3 volts. Okay, this current of 200 microamperes corresponds to VGS of 3 volts. Okay, let's say the supply voltage is, for illustration, 10 volts. Okay, now the question is, how do I get rid of this current source? Okay, how do I do that? First of all, this current source, it's carrying a current of 200 microampere and it has a voltage of 7 volts across it in this direction. Okay, what I want to show is the distinction between this current source and this voltage source, whereas this voltage source here is supplying 200 microamperes, and if there are other circuits connected, they will be drawing some current I1 and it will be supplying that I1 as well. Okay, the point is, this current source, it's actually dissipating power. Okay, if you remember how to calculate the power dissipated in a two-terminal element, you consider the voltage and current according to the passive sign convention. That is, if the voltage is defined with positive at some terminal, current should be going into that terminal. Then the power dissipated is V times I, and the power generated by this would be minus V times I. And if you follow that, you can see that this current source here, it is dissipating 1.4 milliwatts, whereas this source is generating 10 volts times 200 microamperes, 2 milliwatts, assuming I1 is 0. Okay, now you can't replace this voltage source. Okay, this is a source of energy, whereas this current source, although it could be a source of energy, in this particular circuit the voltage across it is such that it's actually dissipating power. It's a dissipative element, so presumably it can be replaced with another dissipative element, and the obvious candidate is the resistor. Okay, so now can we replace this with a resistor? I am sure you remember what is known as substitution theorem from basic electrical circuits. The substitution theorem says that if you have a circuit with some resistor, it has a voltage VR across it and a current IR through it, and of course R will be equal to VR by IR by Ohm's law, then you can replace the resistor with a voltage source of value VR or a current source of value IR without changing any of the node voltages or currents in the circuit. Okay. If you don't recall this, go back to basic electrical circuits and then find out about this theorem. This is known as substitution theorem. Okay. So essentially a resistor can be replaced by another element which has the same voltage and current across it. By the way, this is not a general substitution. This is only for particular values of sources that are used in the circuit. Okay. You have a circuit with some voltage sources and current sources. They have some particular values. Only for that particular set of values you could replace a resistor with a voltage source or a current source. Now it turns out you can also go the other way around. If you have a circuit with some voltage source or a current source, you can replace the voltage or current source by a resistor, provided that the source is dissipating power. Okay, otherwise you would have to replace it with a negative resistance and you could get some singular conditions. But if you have a circuit where a current source is dissipating power, you could replace it with a resistor. And what resistor should you replace it with? It should be such that the voltage across it and current through it are exactly same as in the original circuit. Okay. So for instance, in this case, in this operating point, remember this substitution theorem is true for a particular value of source voltages, that is at a particular operating point. So at this point we have 7 volts across it and 200 microamperes through it, and we want to replace it with a resistor, and the resistor also must have 7 volts across it and 200 microamperes through it. But of course a resistor is governed by Ohm's law, so if a resistor has to have 7 volts across it and 200 microamperes through it, the value of the resistance has to be 7 volts divided by 200 microamperes, which is 35 kilo ohm. Okay. So what you can do is you can get rid of this current source, okay, and replace it with a resistance of 35 kilo ohm, and you will get exactly the same current. Now if this problem were given to you as an analysis problem, in fact I would encourage you to solve for it like that. You just take this circuit, let's pretend that you don't know what the current is, and solve for the current. You have to solve a quadratic equation and it comes out quite easily, and you will see that that will be 200 microamperes. Okay. So whether you had a 200 microampere current source here or a 35 kilo ohm resistor, you will get exactly the same current. Okay. So this is used many times. In this particular context, we are looking at replacing current sources by resistors. So let's say you have a circuit and you have a current source of value I0 somewhere, and the voltage across that is some Vx, let's say, and Vx is greater than 0. It's only in that case that this will be dissipating power and you can replace it with a resistor. Then you can replace the current source by a resistor Rx, and the value of Rx of course has to be equal to Vx divided by I0, and the conditions in the circuit, that is the voltages and currents in the circuit, will remain exactly the same. Okay, and this can be done for any circuit. All of the biasing circuits that we discussed earlier, for particular values of supply and so on, you need to know the numerical values of everything. Then you can replace the current source in those biasing circuits with a resistor, and the bias conditions will remain exactly the same. Okay. Now if a resistor is as good as a current source, then why would you ever want to use a current source? Now not everything is exactly the same. Okay. For instance, let me take the circuit again. So I had a 10 volt source and a 35 kilo ohm resistor, okay, and I have my original circuit with a 200 microampere current source. Okay. So now let me call these M1 and M2. Remember, the whole idea of using constant current biasing was to reduce the sensitivity of the transistor's transconductance to the parameters of the transistor, such as the threshold voltage and current factor. Okay. Now that sensitivity will be different for this circuit and that circuit. Okay. So let's say the threshold voltage of M2 changes by some amount. The current through it will still be exactly 200 microamperes. Okay. So the transconductance of M2 doesn't change at all. This is the easiest example to consider. So let's say Vt increases. M2 has a current of 200 microamperes and Gm is 200 microsiemens. Basically, neither of these changes. Okay. Whereas in this case, if the threshold voltage increases, and if you carried out that earlier exercise I mentioned of trying to solve for the current here, you will see that the current will change. ID will actually reduce slightly and Gm also reduces. It is still very likely to be much better than constant VGS biasing, but it's not as good as biasing it with an actual current source. Okay. So a resistor is really a poor man's current source, but sometimes just for the sake of convenience you can use that. Okay. And as you can guess, the equivalent resistance, the incremental resistance of a current source is infinity. So the larger the value of this resistance, the more closely it approximates a current source. Okay. So for instance, that you also know from Thevenin and Norton equivalents, if you have a large voltage and a large resistance in series with it, then it behaves more or less like a current source for small values of load resistance. Okay. So exactly the same thing works here. If this resistor happens to be very large and if this voltage is very large, then it will tend to behave like a current source. Okay. So that's one difference. The sensitivity is actually worsened when you use a resistor, and also there is additional sensitivity to something else. Okay. If you change the supply voltage 10 volts, what happens to M2? Absolutely nothing, because it doesn't even see the change in that voltage. All of that change will appear across this 200 microampere current source. Okay. So there will be no change in the current or transconductance of M2. Whereas if you change the voltage to M1, if you change the supply voltage, M1's current will change. If this becomes 12 volts instead, the current in M1 will increase. Okay. So the sensitivity to supply voltage will be 0 in this case and non-zero in that case. Okay. So this is inferior to having a constant current source, but it is superior to having a constant VGS. Okay. The motivation to use this is simply to avoid current sources, especially in case of discrete circuits. The analysis of sensitivity and so on, you can carry out in activity and assignment problems. Okay. Then you will clearly understand why and by how much this is worse than that one. Okay.